Welcome to our team's project on homework 5, where we implement latent denoising diffusion probabilistic models. Okay, so in this presentation, we will go through the problem statement, the task, the approach, the results, and then look at the conclusion. Okay, so regarding the problem statement here, we are looking at diffusion models, which are powerful generative models that have revolutionized the Gen AI field. These models work by adding random noise to datasets, then learn how to reverse this process and remove noise iteratively. In learning how to predict noise, diffusion models can reconstruct data from a noisy version. Diffusion models have applications in image synthesis, data restoration, and media content generation, even robotic manipulation. Addressing inefficiencies and enhancing these models makes them more applicable for real-world use cases, such as scalable and controllable image generation for industries like gaming design and advertising. This project aims to implement and improve denoising diffusion probabilistic models, DDMs, for generating high-quality images. Diffusion models are computationally intensive and require optimization for practical deployment. We are solving the challenges of improving inference speed, computational efficiency, and image quality by integrating additional advanced methodologies such as DDIMs, VAEs, CFGs, and we have followed the homework 5 write-up to do so. Furthermore, we do exploratory work by altering the linear DDPM noise scheduler. This investigation can lead to potential improvements in model performance, efficiency, and robustness. So looking at the task here. So our work is to primarily re-implement the following methods. The first is DDPMs, or denoising diffusion probabilistic models, which are generative models that progressively add and remove noise to learn high-quality data construction. We treat this as our baseline and benchmark. We then implement DDIM, which is an extension of DDPM that accelerates inference by reducing the number of reverse diffusion steps. We then implement a VAE to create a latent diffusion model. This is a method that reduces computational costs by performing diffusion in a lower dimensional latent space. Lastly, we do classifier-free guidance, which is a technique for conditional imaging generation that integrates conditioning directly into the diffusion model for greater flexibility and control. Lastly, we implement our cosine noise scheduler for the exploration portion of our project. Okay, so looking at the data set here, we use the ImageNet 100 dataset, but do also use the CIFAR 10 dataset to train sort of our intermediate models. For our final combined model, though, we use ImageNet 100. So looking at the approach here, DDPM, we start with DDPM. It follows a UNet architecture, which has an encoder, bottleneck, and decoder. For the training objective, we do a forward process that adds noise based on a pre-computed scheduled beta, and a reverse process that learns the noise incrementally. We're training based on MSE between the predicted and actual noise. For inference, we begin by drawing a sample from a Gaussian distribution and then iteratively apply reverse diffusion steps here. The result is we try to generate high-quality coherent images. For DDIM, we improve upon DDPM by introducing this deterministic reverse diffusion process, and we are able to replace DDPM's reverse step with this non-Markovian sampling, which is important because it allows us to skip the intermediate steps that DDPM uses. And instead, we're now, each time step is depending on the model's noise, prediction, and deterministic reverse step formulation to avoid randomness. You can look on the right to see how we compute this process. For VAE, in the next step, we look at VAEs and CFGs. For VAEs, we already have a pre-trained model provided in the assignment, and so we use this VAE to train the latent DDPM. For CFG, this simplifies conditional image generation by eliminating the need for a separate classifier. Instead, the model is trained to handle both conditional and unconditional generation tasks. We adjust this guide in weight W. Lastly, for the cosine noise scheduler, we follow this process here and replace the noise scheduler where it's ordinarily linear. For our results, we find that our performance, so starting with the baseline, we achieve an ID score of 8 and an inception mean score of 3.31. We measure performance based on these two scores, which measure the quality and diversity of generative models. Lower FID and higher inception score indicates better performance. Currently, DDIM plus CFG performs the best relative to our DDPM benchmark, and the DDIM plus CFG plus VAE underperformed here for two reasons. One, it did not train long enough, and a unit model did not have sufficient capacity. In the final report, we will sufficiently train to have final results, where we expect the DDIM and CFG plus VAE to outperform. DDIM with cosine noise scheduler performed better than DDIM plus CFG on inception, but worse on FID. These are preliminary results, and we will be further explored for the report. Here are just some snapshots for DDIM, where we are able to show the output is starting to look like coherent images when we do inference. Now DDIM plus CFG snapshot, images are looking pixelated but not pure noise, and they're looking slightly better than the DDPM results. And then the DDIM plus CFG plus VAE, the inference images are almost pure noise right now, but we can see that after 10 epochs, the images being generated from the training data do not look like pure noise. So we think that this model is working. We just need to train it for longer to see how it does. And then lastly, the cosine noise scheduler right now is not looking great. It yielded noisy images during inference, so we need to continue doing fine-tuning for the final report. In conclusion, DDIM plus CFG outperformed the baseline DDPM in terms of FID and inference efficiency. DDIM plus CFG plus VAE underperformed, but we believe this is because of limited model capacity and training time, which we will continue to do for the final report. For the noise scheduler, the cosine noise scheduler shows promise, but further fine-tuning is needed. In terms of our real-world impact, being able to show advanced configurations like DDIM and CFG plus VAE can deliver high-quality image synthesis with faster inference, especially when combined with a better noise scheduler. Thank you.